Okay, we are in the last video in the Kalman filter equation series. These are the full Kalman filter equations that I got from Wikipedia. So far we are familiar and understand the first two. Moreover, we understand that mu expected, yes, and sigma expected, as we can see from the sensors, are like this. This video will be devoted to the last 5 equations, okay? So let's start. If you remember from the last video, we have the state space and then we move to the sensor space. So this point over here will move to this point over here. But this is not so simple. Why? Because sometimes our sensor is noisy. So the transformation from the state space to the sensor space includes uncertainty. This uncertainty comes as a result of the physics of the sensor. The sensor measures what it needs to do, but it contains inherent noise. We will call the covariance of this uncertainty, i.e. the sensor noise, Rk. The distribution has a mean equal to the reading we observed, which we call Zk. So Zk is the measurement that we are getting from the sensors. And again, it could be in 1 dimension, 2 dimension, etc. So Zk is the measurement from the sensor. And again, the measurement is a vector, so it can be 1 reading, 2 reading, etc. And Rk meaning the uncertainty or the covariance matrix. Each sensor has its own covariance or uncertainty. Why? Because each sensor includes inherent noise that comes from its physics. In one hand, I have the prediction as stated in the sensor space, which is this point over here. Let's call this point hk times xk. Okay? On the other end, I have the actual measurement, which is Zk, and Zk also has its own uncertainty, or R matrix. So the green blob is the prior, the blue blob is the measurement, and we want to combine, to multiply them together to get into the posterior, which is this part over here. I want both the prediction as represented in the sensor space to be true and also the measurement Zk. So if you remember, we did exactly the same thing in the 1D Kalman filter. And since the 1D Kalman filter is exactly the same as the multidimensional Kalman filter, what I would like to do now is to recap the one-dimensional Kalman filter and then to show you that the scary and complex equations are just a matrix extension of the equations that we are already familiar with. Let's start. If you remember, when I have two Gaussian distributions, one around mu0 and the other around mu1, one with variance of sigma 0 square and one with a variance of sigma 1 square. So if I want to multiply mu0 with mu1, the first PDF with the second PDF, if I want both distributions to hold true, what I end up with is a third normal or Gaussian distribution with mu prime and sigma square prime. And the definition or the mathematical transformation from the first two to the third goes like this. Here we have the PDF or the Gaussian PDF of the first distribution. Here we have the Gaussian PDF of the second distribution. And if I multiply those two together, I will end up with a new mu and a new variance. So the new mu, the new mean, will be expressed as mu0 plus sigma 0 square, mu1 minus mu0 divided by sigma 0 square plus the sigma 1 squared. And the new variance, the new uncertainty, will be sigma 0 square minus sigma 0 to the power of 4 and divided by sigma 0 square plus sigma 1 square. Now, if I arrange or play a little bit with the math, what I'm getting is the following. The new sigma, mu prime, equals to the old sigma, sigma 0, plus k, mu 1 minus mu 0, if I define k as follows. And the new uncertainty, the new variance, equals sigma 0 squared minus k sigma 0 squared. And again, we have already discussed it because k is like the knob that we switch to give more weight to the measurement or to the prediction. Switch k to 1, I will give more weight, more importance to the current measurement. And when I switch k or the knob into 0, I will give more weight or more importance to the prediction. Now, these are the 1D Kalman equations, and we are already familiar with. Now, let me show you how these equations can be exactly extended to multi-dimensional matrix notation. On the left, I have mu1 and sigma 1. This is the measurement. And mu1 has the mean zk, which is the actual measurement from the sensor, and the uncertainty matrix Rk, which we get from the sensor datasheet. On the right, we have mu0 and sigma 0. This is the prediction of the current state as expressed in the sensor space. And we know that the mean of mu0 is hxk, and the covariance or the P matrix is hk p hk transpose. The new mu is mu0 plus k mu1 minus mu0, which is identical to the one-dimensional scenario. And the new sigma, the new uncertainty, equals sigma 0 minus k sigma 0. So let's do it slowly but surely. So mu0 over here is basically hk xk plus k, okay, mu1, but mu1 is zk minus mu0 hk. So basically what I'm having is hk times xk, which is mu0, plus k zk, which is mu1 minus mu0 hk xk. I know what you're thinking. You're saying, yes, but this is not the new state vector since we are having hk xk and not xk. You are absolutely correct, but we need this hk. We need this transformation from the state space to the sensor space because we measure the sensors in the sensor space. In other words, the right part of the equation happens in the sensor space, thus the left part of the equation must also happen in the sensor space. But don't worry, we will get rid of this hk later on. Okay, now what about the new uncertainty? What do we know? We know that the new sigma equals sigma 0 minus k sigma 0. And this is exactly what we are getting here. Okay, sigma 0 hk pk hk transpose minus k sigma 0. And what is k? K is, if you remember, sigma 0 divided by sigma 0 plus sigma 1. Now, since we are dealing with the matrix notation, we don't divide by sigma 0 plus sigma 1, we just look at the inverse. So let's see what we are doing. So this is sigma 0, okay, hk pk hk transpose times sigma 0 plus sigma 1 to the minus 1, or the inverse of this matrix. So these are the new multidimensional Kalman equations that are exactly like the one-dimensional case. Now again, I owe you one more thing. I owe you to get rid of this hk because I need to get these equations back from the sensor space to the state space. How do I do it? A simple rule from linear algebra. I can divide every element of the equations by hk. So let's see how it's done. This will be equation number 1, this will be equation number 2, and this will be equation number 3. So again, I'm going to divide every element in those equations by hk. So on the left side, I'm going to get rid of this. Now I'm going to get rid of this, and in the k, if you remember, I'm going to get rid of this. So equation 1 becomes xk, the new posterior state vector estimation, after we incorporated the prediction of the motion model and the measurement, is the posterior of xk equals to the prediction of xk, which is, if you remember, yes, f of xk minus 1 plus bk times u plus k zk minus hk xk. And I'm going to do the same thing for the uncertainty p matrix. I'm going to divide everything by hk. So over here, I'm going to take this part, and this part, but this time I'm going to divide also by hk transpose on the other side. So I'm going to get rid of this, get rid of this, and get rid of this. So the new uncertainty becomes pk minus k times hk times pk. We just got rid of the first hk, so the new k is pk hk times hk p hk transpose plus rk to the minus 1, or the inverse of this part. So when we are finished, we just finished explaining all the complex and complicated Kalman filter equations. So please pay close attention that what we end up with is identical to the equations that we showed on the Wikipedia page. The only difference between the equation that we ended up with and the equations on the Wikipedia page is that Wikipedia defines yk as zk minus hk xk. So basically it's going to be yk. And there is one more thing. Wikipedia also defines this part as sk. So the new k, the new Kalman gain, is basically pk hk times s to the minus 1. So basically we are dealing with the same set of equations. So ladies and gentlemen, we just finished explaining the complete Kalman filter equations, and I know that many people are terrified from the Kalman filter just because these very equations. And I know that many students are terrified by the Kalman filter just because of these very equations, but not you and not anymore. Now you not only understand these equations, but you know how to derive them from the 1D Kalman filter scenario. In the next section, we are going to take everything that we have learned so far and program it into a solid Python program. Good luck!